All right, so what we're going to do then here today is sort of what we did with discussion on Monday. And we're just going to go over some of the stuff out of chapter 1, not every single thing. You should review chapter 1. There's a lot of sort of math stuff in there. It's a math review, and we're going to talk about scientific notation and how to do it on your calculator, which is really important. And that's kind of the main things out of this chapter. So let's get into it here. So obviously, as we've been talking about, chemistry does sort of impact all kinds of our areas of our life. Crime labs, obviously, use chemistry. Regular sort of labs, even like, food things use chemistry. There's food chemistry and that type of stuff. As we talked about before, really all of chemistry really involves around really the study of matter. And again, as we talked about, matter has basically anything that occupies space and has mass. So that's pretty much everything, anything you could touch, kind of see, maybe even not see, is really matter. And one of the main things that we look at in chemistry is really the sort of changes in state that occur with matter. And there's really 3 types of matter or states of matter that we come across. One is solid. So in the solid state of matter, everybody is pretty much in there pretty tight to one another. They're packed in. They're usually very dense in there. There's not a lot of energy sort of going on in the solid state, so things aren't moving past each other. They're kind of locked into place. The other state of matter is liquid. And in the liquid state, they're still fairly close to one another, but there is a little bit more energy. So things are able to sort of pass one another, move around one another. That's why when we think about liquids, they're really fluid, right? We're able to pour them and stuff like that because there is a little bit more energy and they're able to sort of move around. Last state of matter is gas. And in the gas state, pretty much everybody has broken apart from one another. They're flying around the container. They're having collisions that occur with the walls of the container. And that's what causes pressure, as we'll talk about in a later chapter. And they're flying around with a lot of energy. So kind of gas has a lot of energy, solid, not so much energy sort of happening, just kind of sitting there. So sort of the different states of matter is a very important part of chemistry, and a lot of what happens as matter sort of changes states is important. So for example, if we go from solid to liquid, that is the process known as melting, right? If we go from liquid to solid, that's the process of freezing. Yeah. We go from liquid to gas, that's the process of evaporation or vaporization. If we go from gas back to liquid, that is the process of condensation. There's also a process where we could go from solid directly to gas and actually skip the whole liquid part of the environment there, and that is what is known as sublimation. And there's also a process where we could go from gas all the way back to solid. Once again, here skipping the liquid, that is what is known as deposition when that occurs. So maybe you're familiar with sublimation if you ever seen dry ice. Dry ice, right, goes from solid directly to gas, no water mess up or liquid mess up, really. By the way, dry ice is really not water. Dry ice is carbon dioxide. So it actually goes from the solid state to the gas state, skips the liquid state. Process of deposition, maybe you've seen a CD, DVD, you could Google them. I think they may still make those things. But they're really shiny there on the top, and that's how they get the metals on there. They actually cool them down. Metals come onto there, makes them really shiny and stuff like that. Now, when we talk about these sort of transitions of state, It also involves energy, which is a big part of chemistry. I think we have a chapter kind of devoted to energy that we'll talk a little bit about. But when we talk about melting and freezing, does that occur at different temperatures or the same temperature? Melting and freezing actually occurs at the same temperature. So it does occur at the same temperature. And that is usually what is referred to as the normal melting point or freezing point of a substance. So for example, water will freeze at 0 degrees Celsius. So exactly at 0 degrees Celsius, you basically have both phases happening at the same time. You have liquid water, you got solid ice happening, kind of like ice crystals. So you got a little bit of both. It's not really until you get a little bit above 0 degrees Celsius that you get into liquid water. It's not until you get a little bit below 0 degrees Celsius that you actually get into full ice. But dead on at 0 degrees, you basically have both of the phases happening. And because it occurs at the same temperature, it's really the energy that's either being applied or released as to sort of which way you go at that point. Do you make ice? Do you make liquid water? Same thing here for evaporation and vaporization and condensation, also occur at the same temperature. And that is what is sometimes referred to as the normal boiling point of a substance. For water, that's 100 degrees Celsius. So again, exactly at 100 degrees Celsius, you got some liquid water, you got some steam sort of happening. Once again, not until you get above 100 degrees Celsius that you really have fully kind of water vapor or gas. Not until you're a little bit below 100 degrees Celsius that you basically have liquid water that occurs. So it's really at those points all about what is happening with the energy as to sort of which way that you go. So for example, if I go from solid to liquid to gas, in terms of energy, do I need to put energy in to do that? Or do I need to remove energy to go from solid to liquid to gas? Energy needs to be, it does need to be added. So if you think about a really simple example of an ice cube, right? You take the ice cube out, what happens to it? It starts to melt because it's picking up all the energy from the atmosphere, right? So it's picking up that energy. Now you got a bucket of water on your hand. You decide, well, I'll make some pasta, right? So you put the water, liquid water up on the stove, you start cooking it. You're adding heat to it, it starts to boil and you start to get steam, right? Which is the liquid water going to gas, right? At its boiling point. And that all involves energy being absorbed or put in. And when energy is absorbed, it is sometimes referred to as a endothermic process. So endothermic means heat and energy being absorbed or put in. And it would obviously be opposite as you go the other way from gas to liquid to solid. As we go from gas to liquid to solid, we have gas molecules that are flying around. We actually have to remove energy. And when we remove energy from gas molecules that are flying around really fast, they are flying around a little bit slower with not as much energy. When they hit each other, they actually stick. They don't have enough energy to escape and they drop into the liquid phase. You continue to remove energy, like take your water and put it into the freezer. You're actually removing energy because your water is actually hotter than the freezer. So all the energy from the water goes out into the freezer to try to cool it, to warm it up. And your water gets colder and colder and colder until it freezes. So that's actually removing energy in that case. And in all those processes, energy is released. And processes where energy is released, those are what are referred to as being exothermic. So when we talk about being at, say, 0 degrees Celsius and you have both phases happening at the same time, if you are exactly at 0 degrees Celsius, you decide to continue to put heat and energy in, you will continue the process of melting and go to liquid. If you're at 0 degrees Celsius and you continue to remove heat and energy, like put it in a freezer, you will go the other way and it will go into ice, for example, for water, and go into the solid phase. Any questions on any of that there? Yeah. They occur exactly at the same temperature. What that means, for example, water. I don't want to go here. Water freezes at 0 degrees Celsius. So when you look at, say, like a heating or cooling curve, something like this, and let's say that this is ice, and this would be liquid water. This would be basically steam or gas, basically with water. So right here at 0 degrees Celsius, this guy would be 100 degrees Celsius. So exactly at 0 degrees Celsius, you basically have both solid and liquid happening at the same time. And that's what it means. You're basically sitting at the point where you have to make a decision. Do you want to continue to melt the ice or do you want to make more ice? If you want to continue to melt the ice, the melting point is 0 degrees Celsius, which means you need to put more energy in. And as you put more energy in, the temperature will start to rise and your ice will start to melt. If you're still at 0 degrees Celsius and you decide I want to freeze it, you put your liquid water or your ice crystals into the freezer. It starts to remove some energy. Energy is being released at 0 degrees. Temperature starts to drop, right? Your ice water will start to freeze and become solid at that point. So that's what it means. It happens at the same temperature. At that temperature is like 0 degrees for water. You're really at a tipping point as to which way you want to go. And it's all dependent on what you do with the energy. If you put more in, you'll go and start to melt. If you take energy out, you'll start to freeze. And the same thing happens right here at 100 degrees Celsius. You're basically in sort of an equilibrium between liquid and gas. And at that point at 100 degrees Celsius, if you continue to apply heat, like if you were boiling the water to make pasta, right? You've got a constant flame going, right? You're continuously applying heat. You will start to have evaporation and that liquid water will go into basically steam, which is the gas version. If at 100 degrees, you decide to shut the water off or the heat off, right? What happens? The thing stops boiling, right? And you're left with cold water eventually, right? So the temperature comes down, you're left with just cold water at that point. So those kind of boiling points and melting points are really the temperature where you can either take it one way in terms of the phase or the other way, depending on the energy that's applied. They really are, and you do have both sort of phases happening there. Also, as you can see from this diagram, it's sort of correct in the sense it takes a lot more energy to go from liquid to gas than it does to go from solid to liquid. As you can see here, it takes a little bit of energy to go from solid to liquid, but much more energy is needed to take a substance from liquid to gas. Why does it take more energy to go from liquid to gas? What happens when you go from liquid to gas? So just in general, when we go from solid to liquid, right? As I drew in those circles at the beginning, right? In the solid state, everybody is pretty much close to each other, tight. In the liquid phase, they're still relatively close to each other, but there's a little bit more room for movement. So it doesn't take as much energy to start getting them to move. But when you do the transition of going from liquid, where they're kind of moving and still really close to each other, to gas, where everybody's completely broken apart from each other and flying around, it takes a lot more energy to get everybody apart into the gas phase and fly around. And that's why you also see, when you look at these curves, and I think we'll see it maybe in that chapter, so a little bit bigger of a curve of a line. It's also a plateau line. It's not going up or down. That means that the temperature remains constant through there, and that's where you have both phases basically happening. Other questions? Okay. So we're going to skip a little bit some of this stuff here. The scientific method we're not going to talk too much about, but the scientific method is really based on a few things, and it really all starts with observations. And it's really like you make an observation about something, and then you maybe tell your advisor about it or whatever it may be, or they make an observation, they go, that's a great idea. I think you go do some experiments on that. So usually when you make an observation, you try to come up with a hypothesis, and a hypothesis is some type of testable type of explanation as to what you actually observe. So a good hypothesis in chemistry is one where you can basically do some type of experimentation to see, is it correct or is it not correct? So that usually leads to experiments, which unfortunately or fortunately lead usually to more observations. And then you go tell your boss, and then you get this great idea, go do some more experiments. And you come up with more hypotheses, and you do more experimentation. Eventually, it can be sort of a vicious cycle, but at some point, usually a couple of things can come out of it. And the two things that come out of it is a law or maybe a theory. And there is sort of a difference between the two. A theory is really something that may be correct in certain situations, but may not always be correct in all situations. So you can kind of think of a theory as something that, well, at one point in time, we felt that it was correct, but maybe further experiments came along and they're like, well, not all of that's right. Some of it's right. The other parts aren't right. So for example, there is Dalton's atomic theory. And Dalton's atomic theory, basically a couple of things out of there is all good, but later experiments showed some other things were incorrect. There's Bohr's model of the atom, for example, or theory of the atom, which works extremely well to explain what happens in hydrogen. But as you move past hydrogen, it really doesn't hold up very well. It's kind of the planetary model where electrons are going around in pretty circles. That's really not how electrons move. Even if biology tells you it does, they really don't move that way. But it doesn't really work very well past sort of hydrogen. So theories are things that, you know, for the most part, explain things, but they can be revised over the years. They can be, you know, told like maybe not all of it is correct. Now, a law, on the other hand, a law is something that no matter what's the situation, always pretty much happens the same way. There is no deviation. There's no like revision of it or anything like that. Like the conservation of mass. So for example, conservation of mass says we don't lose any mass or create any mass in a chemical reaction. And that is why, if you're familiar with, and we'll talk about in this class, balancing equations, for example, if we started with 4 carbons on the starting material, we will end with 4 carbons on the products or what is made as a result of the reaction. They may be in different compounds. They may broke apart the bonds and reform some new bonds. But because we started with 4 carbons that have a mass of about 12 each, and we ended with 4 carbons that have a mass of about 12 each, there's that conservation of mass, and also why we have really the conservation of elements in chemical reactions. There's the law of conservation of energy. Energy is neither created nor destroyed, but it is transferred from one place to the next. So if something loses a certain amount of energy, somebody else will gain the exact same amount of energy. And these are things that always happen no matter what the situation. So a law is sort of a permanent explanation. It doesn't really deviate, doesn't have to be a certain situation. While a theory can be sort of revised and maybe revisited with further experimentation. Any questions on that there? Okay. All right. It's a nice picture of a cat. All right, we'll continue on. All right, let's see. Let's talk a little bit about some math skills, which is a part of this chapter. And again, we touched upon some of these things today. It is good to obviously understand what each of these sort of numbers represents. So that's the thousands place, right? Hundreds, tens and ones place. Also decimal places. So that's your tens place, your hundreds and your thousands. Obviously, that's your ones place. As we talked about today, it's important to take your measurements and stuff to the proper number of digits, as they are important and significant figures. We'll go through here some of these things. Other things that we commonly come across or sometimes come across, right, is, you know, we have positive numbers and negative numbers. If it's a positive number, then obviously you do not need to write the positive sign. And if it is a negative number, you definitely should make sure you include the negative number when you do write it. We also sometimes need to multiply positive and negative numbers together, right? If we multiply 2 positive numbers, we end up with a positive number. If we multiply a positive and a negative number, we end up with a negative number, right? If we multiply 2 negative numbers, we end up with a positive number, right? So when we do come across negative signs and stuff like that, even with adding and subtracting and multiplying and dividing, we do want to make sure we just don't sort of ignore those things. They do affect our values that we get. Also, basically, negative when we're adding and subtracting. So if we had 3 minus 2 is 1. If we had 3 plus -2, that is also 1, right? It's basically the same thing as subtracting. If we had 2 negative numbers, 3 minus 3 is -6. So it is always important to keep the negative on your values if it happens to come out negative. And obviously positive, you again don't need to write the positive. Same thing goes with dividing. Obviously, we divide 2 positive numbers, we get a positive number. 2 negative numbers, we get a positive number. And if we divide a positive and negative number, we also get a negative number when it's all said and done. As you can see there. All right. And there's our addition. Let's talk a little bit about calculator operations and some important buttons on your calculator. I see this one picture, so I'll circle it here. So most calculators, scientific calculators that you need should have some really important buttons for this particular class. We're going to talk about how to use them properly in just a second, but there's actually negative buttons on most calculators, and it is the button that either usually looks like that, a plus and a negative, or it is a button that usually looks like that, which is also your negative. You do not want to use your subtract button if you're going to punch a number in that's negative into your calculator. More importantly is the exponent button when you want to do something like scientific notation. That is usually a button that's an EE button, an EXP button. And if you have kind of a two-tone calculator, you will maybe have a button like this, and probably with it a will that looks something like that. Yeah. Usually it's like the blue and white outside or some type of calculator like that. So those are really important buttons, and more importantly, you need to know how to use them properly, because we will use these buttons along the way. We also will use the log button in later chapters. So these are all some of these buttons, and you want to make sure that you do use them properly, and we'll get to that in just a second. Let's also talk about when we are putting numbers into a calculator. Let's say, for example, we had a problem where we want to take 55 and we want to basically do a bunch of math here. We want to take 36, we want to go 12, maybe 6, just making up numbers, and we'll go 16. So when we have something set up like this, which is what is referred to as dimensional analysis and how you should set up stuff, and we'll talk about it in chapter 2 a little bit more when we get there. But basically, mathematically, what we're doing here is every number that's on top, we're going to multiply. And then we're basically going to come back and divide by all the numbers that are on the bottom. Now, what happens with a lot of people in their calculator is they decide they would like to put all the numbers in at once, which is perfectly fine if you understand how to punch it in correctly with parentheses and all that good stuff. In my experience, most people do not know how to do that properly. So when you have a situation like this where you're going to be multiplying a bunch of numbers, and then you need to really come back and divide by a bunch of numbers, here is really the best way to do it, and you usually will get pretty much the right answer all the time. You could multiply as many numbers as you want on top. So in this case, we would type in 55, hit our multiplication button, type 36, hit our multiplication button, hit 12. That comes to our end of everything we're multiplying up on top. You should hit the equal button at this point. We then really want to come back and divide by all the numbers that are on the bottom. So you would then hit divide by 6, and then you should hit equals. And then you should hit divide by 16 and then hit equals. And you will always get the right answer. Again, if you try to punch it in 55 times 36 times 12 divided by whatever it is there, 6 divided by 16 with no parentheses or anything like that, your calculator is most likely going to do the wrong math. And people are always amazed, like, I don't understand how I got the wrong answer. I got it all set up. And a lot of the problem comes with somebody trying to like punch way too much stuff in there. So usually you're pretty safe to multiply as many numbers as you want on the top, but just make sure you hit equals at the end, and then really just go by each number individually and divide by each number, hit equals after each time. You're probably guaranteed to always get the right answer if you follow that approach. If you don't follow that approach, well, maybe you'll be lucky or maybe you won't be lucky, but you might get the right answer. Another very common thing that we sometimes come across are percentages. And sometimes we do need to kind of convert percentages into like a conversion factor to use in a calculation. So for example, if I had something that was 5.5% by mass, calcium chloride, what that really means when you have a percentage and you want to turn it into a usable number, you should assume you have how much of it? 100, right? Kind of like on your exam, you got an 80 on the exam, you probably got 80 points out of 100, right? So it keeps the numbers the same. So for example, if we were to kind of convert this into a usable sort of conversion factor, we basically could just say it's 5.5 grams of calcium chloride and 100 grams of solution. So that's basically 5.5%. So it's a much easier way to do that. And if it was a conversion factor, we could flip it around and use it the opposite way. And when we talk more about conversion factors in chapter 2, but we could say 100 grams of solution gives us 5.5 grams of calcium chloride. So it's much easier to assume that you have 100 or something when you want to kind of convert a percentage into a usable number. You could assume however much you want, but you have to change all the numbers. So that's not very helpful to do. And that's obviously how they get 59.6% here by dividing these two, times it by 100, gives you the percentage, in this case, of how much aspirin there is in a tablet of aspirin. That's also how we get 5% red balls, 5 red balls of 100. And over here, they're missing the times 100%. So 50 green balls over 100 total balls is 50% green balls in this case. So that's a very common thing that we do come across a lot, which is sort of converting percentages into usable number. We might not come across too much of this kind of straightforward algebra type of situation, but we do come across rearranging formulas and stuff like that you need to do. But in general, in algebra and the equal sign, hopefully you're familiar with, but in case you're not, if you need to move something to the other side of the equal sign, you basically do the opposite operation of what's happening to it. So what I mean by that, that is +8, which means if I want to move to the other side, I need to subtract 8 from both sides. That gets rid of it. That leaves me 2x is equal to 6. Now I want to get rid of the 2 to the other side. 2 times x is basically what I'm doing here. So I'm multiplying to move it to the other side. I need to divide to the other side. So it's always opposites when you kind of move something to the other side of the equal sign. If you're just rearranging an actual formula and not really solving for an actual value like this, when you rearrange a formula and you move across the equal sign, everybody ends up in opposite locations of where they started with. So for example, here, if we have P1 V1 equals P2 V2, and we want to solve for V2, basically these are fractions. They're actually over 1, although we don't usually write the 1. But basically here, we need to move the P2 to the other side. It's up on top. It should end up on the bottom. And that would give us P1 V1 over P2 equals V2. So anytime you're sort of solving a formula like this, and it happens a lot in the gas chapter, there's a lot of sort of gas laws like this that you need to rearrange. Basically opposites move across. So if I had like V1 T1 equals V2 T2, and I wanted to solve for V2, I should move T2 to the top, opposite side, right? It's on the bottom, move it to the top, gives me V1 T2 T1 equals V2. Yeah. Any questions on that there? We're basically multiplying and dividing is what we're doing, right? But the quick way is just to move it to the opposite side. So in this case, we're actually multiplying both sides by T2. And that's really how it gets to the other side, is multiplying by T2, and it cancels out on the other side. Now, what happens if I want to solve for T2? What would it be? Take a second and see what you come up with. When we're solving for something like this, right? Whatever we're solving for should be on the top or bottom usually. Should always be on the top, right? So what that really means is we actually need to move this to the other side first. And that would give us V1 T2 is T1 is equal to V2, basically. And now we have actually our T2 up on top, which is exactly where we want it. That means what do we need to do with the other guys on the left there? We need to move it to the other side, right? So our V1 would then go to the bottom, our T1 would go to the top, and that would give us T2 is equal to V2, T1, V1. Again, opposite locations. It's a very common mistake that some people will make when they go to rearrange this. They'll go, and they'll just go, okay, I'll just move this guy to this side, and that will give me V1, V2, T1 is equal to, does that equal T2? Actually equals 1 over T2. Yeah, it's the inverse of it. Actually, then you flip everybody around. So whenever you're solving for one variable by itself, it always should be up on top. And then if you need to, move everybody back to the other side. Again, here we're still multiplying and dividing everybody to the other side. Any questions on that there? If that is an issue for you rearranging formulas, we do need to do that in this class, obviously. So you do want to, as we get to those chapters and those formulas, you know, make sure you take some time to make sure you know how to properly sort of rearrange things so you could solve the problems correctly. All right. We pretty much are not going to interpret graphs. So let's talk about scientific notation. So scientific notation, which is really one of the main things that you should get out of chapter 1 here. Scientific notation is a way that we write numbers so that we can handle really large numbers and really small numbers. It has a general formula of n times 10 to the n. And this guy needs to be a number between 1 and 10. It cannot be less than 1, and it cannot be 10 and above. So it's got to actually be a number between 1 and 10. So it's got to be 1 point something all the way up to 9 point something. It cannot be, again, 10, 20, 100, or point something. That first number has got to be between 1 and 10. This number here is either going to be a positive or negative number, and it's based on how far you got to move it to actually get yourself to a number between 1 and 10. So for example, the reason we do this is there's a lot of numbers that have a ton of zeros and stuff in it. Like if you did something like Avogadro's number, you're like a bunch, I don't even know how many zeros there are. There's like 20 some odd zeros. There's a lot of zeros. So if you were trying to do some type of calculation with that, you're definitely going to lose some zeros along the way. Or if you have really small numbers, right, with a bunch of zeros at the beginning or something, you know, you're going to probably maybe mess up. So we do use scientific notation to get us some, you know, nicer looking numbers. We hopefully won't lose numbers along the way. So for example, here, if I had 3, 2, 5, 6, if I wanted to make this into scientific notation, we would assume the decimal point would be at the end, and we would go one place. That gives me 325. That is not between 1 and 10. I go one more place. That is 32.5, which is not between 1 and 10. I go one more place. That is 3.256. That is a number between 1 and 10. This would be 3.256 times 10. I moved it 1, 2, 3 places. It would be a positive exponent because it's a large number. So large numbers have positive exponent. By the way, I kept all those numbers because this number has how many significant figures? 4. When I wrote it like this number has now how many? 4. Remember, all the numbers before the times 10 part are significant. So once again, you never want to lose significant figures as you go from scientific notation to decimal or back and forth. If I have a number like 0.004320, I would move it one place, not a number between 1 and 10. One more place is 0.4, still not a number between 1 and 10. One more place there gives me 4.320 times 10 to the minus 3. Negative exponents are for small numbers. So smaller numbers have negative exponents. Once again here, this number has how many significant figures? It does have 4. It would be all these guys. So when I turned it into scientific notation, I still kept the 4 significant figures. So again, you do not want to lose any significant figures when you do it. As we talked about earlier today, you can basically control the number of significant figures by writing a number in scientific notation. And again, it may be the only way to get the proper number of significant figures is to actually write in scientific notation. So if I had 3, 2, 6, 4, 9, and I had 0.0032, why don't you write them both in scientific notation real quick? Okay, let's take a look. So we would assume decimal there. So 1 place, 2 places, 3 places, and 4 places we would need to move. That gives us 3.2649 times 10 to the 4th. Once again, we would keep all the numbers there so we do not lose any significant figures. Bottom number there has 5. Top number in scientific notation also has 5. Any questions on that one? Coming this way, we need to go 1 place, 2 places, and 3 places. Gives us 3.2 times 10 to the minus 3. Once again, here only has 2 significant figures, so does our answer there. Any question on any of those 2? Now, if we did have a number of scientific notation like this, the 2 tells us how many places we need to move the decimal place if we want to turn it into a decimal. In this case, it's a positive 2, which means we need to actually move the decimal place to the right to make a bigger number. And we would go 2 places, 1 and 2, and we would add a 0 in that case. And we would end up with something like 150 there, right? Should I put a decimal at the end of it? I should not, because the scientific notation has 2 significant figures. Write in like that, the 0 is not going to be significant at the end, so it would still have this proper number of significant figures, or scientific notation and significant figures. By the way, your calculator doesn't always give it to you in scientific notation, so unless you have a program to do so. Do you have to give the answers in scientific notation all the time? The answer is no, unless it specifically says to do so. But again, as I mentioned, sometimes the only way to do it properly is scientific notation. So you don't have to do it, but you do have to do everything to the proper number of significant figures. More importantly, though, is how we actually punch these things into our calculator. So let's say we had a number like 6.25 times 10 to the minus 12, and I wanted to actually punch that into my calculator correctly, which would be a good thing. So if we were going to actually punch it into our calculator, we want to use those buttons we talked about before, our exponent buttons, which depending on your calculator is one of these guys. 10 to the end with the will. And we also want to make sure we use our negative buttons, which is one of these buttons here. So if you're going to punch this in properly to your calculator to use in a calculation, you would punch 6.25. You then would hit your exponent button and no other button but your exponent button. That will most likely put up a 6.25 if you have an E, or it may put up a 6.25 and a couple of zeros up on top, maybe a small 10, depending on your calculator. When you hit the exponent button, the EE button, the EXP button, any of these exponent buttons, that represents the times 10 part of the number, which means you do not need to hit the multiplication button. You do not need to hit inverse log or shift log or anything dumb like that. You just need to hit the exponent button. What is left is actually to put in negative 12 at this point. So we want to make sure that we actually use our negative button, not our subtract button. And when you do that, that will put a negative there, or probably put a negative right about there. And then you would put 12, and that would put a 12 there and convert that into a 12. That would be the proper way to punch it in scientific notation in your calculator. Any questions on that? Now, if you have this button here with the little wheel and it's a two-tone type calculator, you have to do one other thing. Because your calculator, frankly, is programmed crappily, you need to actually help it out so it understands how to do it properly. You actually have to put parentheses around all your numbers that you put in scientific notation. So if you have this times 10 to the end button and that little wheel, and it's usually, like I said, kind of a two-tone calculator, white and green or white and blue, you would have to put parentheses to start with. You would need to put 6.25, and then you would actually hit your times 10 to the end. When you do that on your calculator, it will show 6.25 with the parentheses. It will actually put times 10, and you'll have like a blinking cursor up there up on top. Then you're good to go with the rest of it. You would hit your negative button and 12, and it will then turn your blinking cursor into 6.25 times 10 to the minus 12, and now your little cursor is blinking next to the 12. The problem with that is it's still up high and not low. So that is actually where the wheel comes into play. And if you hit that little button there on the wheel, it will bring your blinker down to regular size. And now you can close the parentheses after you do that. And you will end up with something that looks like this, with normal size parentheses at the end. If you do not hit the little wheel part, you will end up with little parentheses on the right and bad parentheses on the left. And a lot of calculators, you'll get an error. So you got to kind of drop it down. So if you do have that button, not a big deal. You just got to kind of put parentheses around any number that you put in scientific notation. If you have the EE button, the EXP button, you don't have to worry about it in most cases. You can just roll through without parentheses. But that is the proper way to punch it in. Any questions on that? So let's make sure everybody knows how to properly punch it in. Let's do these two problems right here. So punch those into your calculator, make sure you use your exponent button and see what you come up with. Okay, let's take a look since we're kind of to the end here, just to make sure everybody punches this in correctly. So if we're going to do the first one there, this is how I would punch it into the calculator. I would hit 6.2. I then would hit my exponent button. I then would hit my negative button because it's negative 11. And I would put 11, and that would get me this number correctly. Again, there's no multiplication button or anything hit yet. I am now going to hit the divide button because that is what I'm doing. And I would punch in 3.7. Once again, hit my exponent button. And in this case, it's actually a positive exponent, so I don't need the negative. I'm just going to hit 22 and then hit equals. And if you do that there, you will get 6.2 exponent negative 11 divided by 3.7 exponent, not negative, but positive 22. And you'll get a number on your calculator, something like 1.675675676. And probably really small at the end, it will say something like this. So we would round this, and we'll talk about in chapter 7 how to round it properly, but we're going to round it to 1.7. But more importantly, you do not want to forget the little part there on the right of your calculator, which is very commonly forgotten. And you want to make sure you write the times 10 to the minus 33. With that being said, that is the proper way to write scientific notation. Improper way would be 1.7 and write the E33. That is not the right way to write scientific notation. That's the right way to put it into like Excel in your calculator. But when you're writing, you should write the times 10 part. If you are having trouble, usually what will happen is this number here, it's all good, but this number is just slightly off, like by 1 or so. And that usually is an indication of how you're punching into your calculator. So once again, a very common mistake people make is they try to hit the multiplication button as they're doing it, or like the second and the log button. You should not use those in this particular case. Any questions on that there? Let's do the next one here to make sure. We're going to go 4.15. Once again, we're going to do our exponent button. We're going to do just 6 because it's a positive 6 here, and that would put it in for that guy. We're going to hit our multiplication button only because we are multiplying, so that's why we're hitting our multiplication button here. We're going to do a 7.7. Once again, exponent button, negative button, and 12 in this case. So that will take care of this guy, and we will hit equals. Now, in this case, we get a number of 0.00003195. And again, we would probably round it to about there. But if we want to write in scientific notation, 1 place, 2 places, 3 places, 4 places, and 5 places, gives us something like 3.2 times 10 to the minus 5. A reminder, your calculator most likely will not give it to you in scientific notation unless you have it programmed. So it's really important to know how to do that. We will come across a lot of numbers throughout the semester that you need to put in scientific notation into your calculator correctly. And it's a super common error on every level of chemistry that I teach, that people do not know how to properly do it. So make sure you use your exponent button. If you have that times 10 with the little circle, you would do the same thing, except that you would just put parentheses around each of those numbers and you should be in okay shape. Any questions on that? If you're not sure where your exponent button is or not sure how to use it properly, just come see me at some point. We will figure it out together. I'll be happy to show you. Other than that, that should wrap up chapter 1.